me. It is based on a paper that came out a month ago or so of the same title, and I'll tell you that. So this is a project about social meaning behavior that affects others on any organismal level. So we can have vampire bats sharing food. We can have dolphin pack hunting sardines. And there's been a number of different theoretical approaches to studying evolution of social behavior. We study it at the level of population genetics, like Marcy did in fundamental work with Mark Feldman. So just look at a gene affecting social behavior. How likely is it to take over the population? Evolutionary game theory, as we've seen a lot of here, is a more phenotypic approach where you're assuming strategies kind of replicate directly based on how they do in interactions. Inclusive fitness is a very individual-based approach, where you look at kind of individual incentives and say, well, if an individual affects the fitness of every other individual by a certain amount, you then multiply it by the relatedness of the actor to the target and add them all up, and that tells you whether that behavior is selected. And then there's multi-level selection, which is less of a concrete method, but has to do with tension between competition within groups versus so I want to try to integrate all of these in some sense, but also deal with the challenge of nonlinear interactions. And I think Jeremy set this up very well earlier. In real world social behavior, especially collective actions among many individuals, fitness depends nonlinearly on the actions of all. So in a sociable weaver nest, they build these large communal nests that persist. But they need to do a certain amount of maintenance or the whole nest falls. Right, so that's just not just like one individual like contributing some fitness amount to another, but it's a collective effort. There's some threshold of effort that is necessary to maintain it. Kind of more dramatic for me is the living ant bridge, where they lay themselves down for others to cross. Half a bridge is not half as useful as a whole, right? So the whole is not the sum of the parts. But these models are challenging to analyze, right? Nonlinearity is always more difficult than linear situations. And in particular, for inclusive fitness theory, there's a challenge of how can one define the fitness contribution of every individual, say every individual ant or bird, to every other in a nonlinear situation where their fitness effect depends on the actions of multiple others. And for me, the inclusive fitness controversy has always been about this question. How do we deal with nonlinear interactions? So we want to model nonlinear social evolution. And I also want to add in populations. So the nonlinear, this is really, I think, a great preprint by Marco Archetti and colleagues that really just argues all situations that we really care about in nature are nonlinear. The title is The Non-Tragedy of the Nonlinear Commons. Great title. And I want to look at this in a lot of different situations that have been considered. So in terms of group selection or family kin relationships or evolution on networks or explicit space or more flexible kinds of social assortment, right? Can we come up with a framework that allows all these different varieties of spice? So this is a kind of abstract framework that I've been developing through a series of papers. I want to briefly lay out here. So we're going to consider two alleles, single genetic locus, and these alleles can live in places. These places are going to be in individuals. They might also have specific spatial locations. Every haploid individual is going to kind of contain one site. Diploids contain two sites for their two alleles. And so we can just record which allele is occupying which site. That's a binary variable, 1 for big A, 0 for little a, and collect them all together into a binary vector or a bit string representing a population state. So in this case, we have 5 genetic sites, and that's how we would represent this population state. And then stuff happens, right? So there's a current state. There's any kind of ecological interaction, nonlinear game, and anything you might want to add. This is where all the spice goes in. And then you have a new state. right? These hard transitions happen. And what I argue is no matter what complexity you put in here, you're always going to have a mapping from the new state to the previous one in terms of how the alleles are inherited. And even if you have a diploid model with asymmetric mating and stuff like that, you'll always be able to map the inherited alleles in the next generation to their parental alleles in the previous generation. And there might be some mutation that occurs that changes the alleles. But as a mathematician, I like to say, what's the abstract thing going on here? And so I'm gonna forget that spice for a moment. Let's just say the thing that I care about is this mapping. So the new allele in each site down there is survived or copied from some allele in the previous site. I'll call that alpha of G. So this is a mapping from the set of sites to its sets. And then we also have mutations that come in. That's going to be a subset of sites that acquire mutations. And we say, well, if a site is not mutated in that transition, then it inherits the allele from the parent. So xg prime equals x sub alpha g. And if it is mutated, then it gets the opposite. Good so far? Feel free to interrupt with questions, by the way. So this is the basic framework. So this happens every time step. And the likelihood of a certain mapping to occur depends on the current population state. So in every state, we get a probability distribution over the pair of parentage mapping and mutation set. And so this proceeds as a Markov chain. There's one main axiom that just says, well, it should be possible for a new allele to take over the population. So you can see like that big A allele is introduced in time step 1 and is taken over by time step 3. It should always be possible for this to happen. Otherwise, you don't really have an evolving population. And we can formalize this axiom, but I won't go through the details. I want to also introduce parameters for mutation and selection. So it's a selection parameter that when it's 0, if there's no selection happening, then this parentage mapping shouldn't depend on the current state, right? So it doesn't depend on what alleles are there. It's just you have a certain probability of inheriting your allele from there or from there. Then there's a mutation parameter. If it's 0, there's no mutation. In that case, we get 2 absorbing states, all big A or all little a. If there is mutation, we get a unique stationary distribution of these states. And so if we're quantifying selection, I'm going to say that whichever allele has the greatest frequency in the stationary distribution is the one that we'll say is favored. So when I say something's being selected, this is the criterion I'm using.
But why is it? Wait, is it obvious that there has to be a unique stationary distribution if there's mutation, or is that?
That follows from that axiom that I breezed over before.
Is that like a primitivity kind of assumption?
Yes, yeah, it's a parent Frobenius, yeah. It's so it's an ergodicity, and it's proven from that axiom of basically complete gene flow. Okay, so this is the basic framework. The allowed spices, what we can include in this model is any kind of population structure. So I haven't said how these sites related to each other. They could be a network, they could be divided into groups. They could be like these two could be together in one individual, one haploid, one diploid individual. Reproduction can be asexual or sexual. Mating does not have to be random. And then any kind of nonlinear fitness interaction is allowed. What is not allowed in this iteration of the framework, we're not allowing population size to vary. We're not allowing the structure itself to change over time. And this focuses only on one locus, 2 locus. So general in some ways, but still kind of rigid in others. Okay, so now we'll start going into results. I do have a measure of fitness. Apologies to Joanna. It's short-term fitness. I'm calling it fitness increments, so avoid attaching myself too strongly to this term. But it records how well my offspring are doing relative to how I'm doing. And it uses these reproductive values, so it's the change in, it's the expected reproductive value of my offspring minus my own reproductive value. If I survive, then this term gets canceled by a term over here. How are these reproductive values are defined? Well, oh wait. There we go. I labeled the terms there. To define the reproductive values, I'm going to specify that for neutral drift, all these fitness increments should be 0. That then gives me a recurrence relation that uniquely determines the reproductive value of each site. So for example, for the death birth model that Alana referenced yesterday, each site has reproductive value that's proportional to its degree. Okay, so we want to allow for nonlinear fitness interactions. And here I'm directly stealing an idea from Jeremy's 2015 paper on short and long-term social evolution, where I'm going to say however the fitness might functionally depend on the current state, I can always write it in the form of a polynomial, where these polynomial terms here are products of the binary variables across some set of sites. So essentially this x underscore s is equal to 1 if all sites in S have the big A allele and equal to 0 otherwise. Right, so this is a unique representation of any function of a binary vector. And the CSG coefficients, essentially they tell you what's the effect of all of some set having the big A allele on the fitness of some site G beyond any effects that are due to proper subsets of S. So we can quantify kind of any degree of synergy using these polynomial terms. And then the other ingredient that we need is a measure of genetic swarm. And so there's different ways you can quantify it. I wanted something that connects to how relatedness is measured in inclusive fitness theory and in other fields. So this is a relatedness measure. It quantifies, it essentially asks, if this set has all the big A allele, what's the likelihood that site G also contains the big A allele? And how much more likely is that relative to any other site in the population containing big A, right? So it's it multiplies, this is all of S having big A, this is G having big A, this is minus the average, population average of A, and it's normalized by the variance of big A in the population, average over the stationary distribution, then the limit mutation goes to 0. So this takes a while to define, but it gives us a nice quantity that agrees with things like siblings have relatedness 1/2. So it agrees with classical relatedness measures in the pairwise case. It also has a nice relationship to identity by descent probabilities and coalescence lengths. Turns out, so the key quantity, if you're going to compute these in the neutral case, you want to find the total branch length of the coalescent tree for your particular set. And you kind of normalize that, and that gets you. Okay, so putting these ingredients together now. So if we have this representation of fitness and relatedness as defined in the previous slide, we get a condition for selection. And it's a sum over all sites in the population and all possible subsets, multiplying their synergistic coefficients by the relatedness. And you can interpret this in a couple of different ways. So you can, the way it's written here, we've kind of separated out the sum over sites. And then the inner term is like, what's the expected aggregation of all fitness effects on that site, taking into account all possible subsets and how they affect that site's fitness? Yeah, Dan.
So relatedness is defined in terms of the equilibrium distribution, right?
The stationary,
Oh, with
the stationary distribution.
Oh, with mutation.
Yes, correct.
Can
Yeah.
I ask you a question too?
Yes.
Sort of, so you calculated the R's under neutrality, is that right?
No, weak mutation, but you have selection.
Is there selection in the calculation of the R?
In the general case, yes. For weak selection, no.
Okay, so then that's what I wondered, because I wondered if the C's had to be small.
Right, so this result holds for any selection string,
Okay.
but I'll get to weak selection in a slide or two. So, and then the other thing that was really interesting to me was that we can take an actor-centric perspective if we allow for collective actors. So if we say like, I'm going to consider this set S of sites as a collective in itself, and say, how does it affect all possible sites in the population, weight that by its relatedness to those sites and add them all up. And that tells me, again, whether my opponent is selected. So what does this do? So this gives us a condition for selection under a lot of different population structures with any kind of nonlinear interaction, right? We can include any kind of polynomial term in my selection and weight it by the appropriate relatedness. Oh, I didn't want to do that. Okay, good. And if selection is weak, then I can compute the relatedness under neutrality using coalescent theory, which is very useful. Otherwise, this thing is true, but very difficult to evaluate. And yeah, this suggests some kind of notion of collective inclusive fitness effects of every set, where you add up its effect on all sites and multiply by its relatedness. This is speculative here. I'm still unsure of how useful this is, but I think it's interesting enough to say. Okay, so now specializing to some more concrete situations. So let's suppose we have, this is similar to the threshold game that Jeremy was talking about, but instead of benefit being shared by a group of vectors, the benefit goes to a particular target that could be inside or outside. So there's some collective S, they can pay a cost C divided equally among themselves to provide a benefit B to either a member or an outsider. And that benefit is only achieved if all the members of this set contribute. Otherwise, nothing happens. And with this, we get a kind of collective Hamilton's rule that this collective action could be cooperation, but also could be spite. It could be a negative benefit. It's favored if benefit times relatedness to the target exceeds cost times the average self-relatedness of S's members. And you might think this looks like a weird term, but it turns out relatedness to self is not necessarily one when you compute it. So we do need a term there for self-relatedness, especially for diploids, right? It depends on who you inherit your alleles from. Okay, so some other situations we can consider. We can suppose that instead of jumping into the river to save his two brothers, maybe Haldane needs to collaborate with two of his brothers to save three more who are drowned in the river. So that would be a collective action dilemma with diploid siblings in some large population. This is our collective Hamilton's rule there. These are the relatedness coefficients under neutrality. So in this case, actually self-relatedness is a half and relatedness to sibling is 1/4. And so then we actually recover the B greater than 2C result, which is the so this validates the, jump into river to save two brothers, but also extends it to two siblings jumping into save four brothers, etc. But what was interesting to me was that this applied to nonlinear situations too. So it might be that, all four brothers need to jump in, sacrifice themselves for those two. It's actually the same condition. which was a surprise to me. We can also consider games on networks of, again, this collective help or harm idea, where they all need to contribute and the help or harm goes to a specific target. And then consider the death-birth process where we choose some individual to be replaced and choose a neighbor to then produce offspring into that spot. We get a slightly more complicated condition here for collective action, where we have the benefits on the left and the cost terms on the right, but they're also weighted by the degrees of the vertices, right? Because remember, that was the reproductive value is proportional to degree in this sense. And then the other interesting term is we get subtraction of, so for the benefit term, we measure the effect on G, but also subtract by this term for G's two-step neighbors. Because when an individual is like, when a site is vacant there, we have two-step neighbors competing with each other to reproduce into this. So then results for various kinds of structures. For a complete network, we get this condition, which is essentially B greater than MC. So the benefit must exceed the group size times the cost, with some correction for finite population size there. We also get evolution of spite to outsiders. It's a weak effect, so it becomes much, it becomes linearly hard depending on the size of the whole population. But in small populations, you get evolution of collective spite. On like a 1D structure, like a cycle, we can get the collective incentivized to benefit its boundary vertices, and more weakly, the two neighbors of those boundary vertices, but really not any others, at least not in a large population. And then there's interesting structures we can consider here, where if we have a central hub, then we can get evolution of really extreme collective altruism, where this peripheral group here is very favored to help the hub node, where K is the number of kind of windmill blades here. And so the left-hand side grows as the number of windmill blade grows, whereas the right-hand side is constant. So if on a large windmill, we get kind of extreme collective altruism. And then similar thing on this more complicated network where we have inner and outer nodes. In this case, one interest, we have an asymmetry where the collective is more favored to help its kind of inner node than its outer. And again, we have possible evolution of spite to far away nodes, which is another interesting point. We can, on more realistic spatial networks, we generated them by Delaunay triangulation, where you throw random points in the square and connect them according to some rule. Marco Archetti used these to model cancer cells and solid tumors, for example. And so we kind of, we used a community identification algorithm and said, what's the incentive for this community to help both its neighbors and outsiders? Some interesting behavior here, where, for example, this community, it is favored to help all of its neighbors at some cost-benefit ratio, and that always occurs. But for example, this one, it's less incentivized to help it than it would be in a well-mixed population. So the spatial structure kind of has a negative effect on helping the more kind of interior members of the collective, because those don't really help the cooperative behavior spread, right? They're less evolutionarily important. And we also see a lot of evolution of potential evolution of spiteful behavior at kind of, in some cases, reasonable cost-benefit ratios. So like, if you have a 5-fold harm, then that can be favored by selection to a distant vertex. Yes, for each one, these are cost-benefit ratios. They're also scaled relatedness as it's called in some papers. And yeah, so some statistics on that. Comparing to a well-mixed population, spatial structure mostly promotes help to community members, but not always. Sometimes it inhibits it. To external targets, it promotes help 17% of the time, usually to direct neighbors, in rare cases to two-step neighbors. To more distant vertices, it almost, or majority of the time, promotes spite or harmful, costly harm, and in some cases does need. We also looked at the spatial networks of sociable weaver nests, where it's reasonable because offspring usually disperse within the nest, at least the male offspring do, and they're the ones who do most social behavior. And similar patterns essentially are found. I'm not going to go into the details on that. So for the more conceptual takeaways, so one thing you may have noticed is that this condition, it looks elegant, but is really rather unwieldy, in that, oh wait, I'm making a different point. Okay. Right, so in principle, every subset of sites is a collective. That's exponential, right? There's 2 to the n possible subsets. However, and I explained that in real world situations, if we take a random set of alleles from a population, they're very unlikely to synergize with each other, right? If it's someone I've never met, you're not likely to have a synergistic effect. And also this relatedness will usually be negligible. So the non-negligible terms are going to be a small fraction of the exponential in many total terms here. The other question you might ask is, okay, so there's this idea that individuals evolved to act as if maximizing inclusive fitness, right? Does that apply to this idea of collective inclusive fitness? And really the answer is no. It's only yes under very artificial circumstances, which I'm not even going to get into. But the reason it's no, the reason collectives do not maximize inclusive fitness is that there's tension between the individual and the collective, or between overlapping collectives, right? So consider how these 3 nodes here, G, H, and I, might affect individual J there. If I'm going to compute that selection, I have to consider how all of these individually are related to J, and also how the pairs are related to the target, and also how all 3 of them together are related to the target, right? So, and selection aggregates over all of those. So we're not going to get any kind of maximizing behavior from any particular collective, and even from any individual, right? If we have nonlinear interactions going on, that, I would argue, really destroys the possibility of inclusive fitness maximization. And instead, we really get more of like inclusive fitness compromise between individual and collective interests. Takeaways. So with nonlinear interactions, we don't have individual causes and effects of social behavior. We can extend the idea of inclusive fitness. And this, I mean, I've spent a lot of my career arguing about the limitations of inclusive fitness. So a lot of those limitations can be overcome, but the actor-centric viewpoint, we can preserve that if we understand actors to be not just individuals, but collectives. And then we can have a kind of collective adaptation, which is not a maximization principle, but which is some kind of compromise over individual and collective interests. And then I've presented this framework for fixed population size and single locus genetics. I do believe this extensions to the more complicated scenarios are possible, but will just require some work. And yeah, I mean, nonlinearity, I would argue, is everywhere. Genetic dominance, for example, is an example of nonlinearity, and so we shouldn't expect kind of simple linear rules to accurately describe what happens in selection. And that's it. Questions? Yes.
I just wanted to do an intuition check. So you said self-relatedness is not necessarily one. And is that just sort of saying that self-relatedness in case of a single diploid is like heterozygosity, or I'm not quite sure what it means when you say that.
Okay. So I'll say that, for example, in a haploid well-mixed population, self-relatedness is one. So for diploids, I mean, it's a question of how we normalize it. So, you know, being a hap means, you know, you inherit your alleles from different places, right? So, you know, if your alleles were always clonal, you know, then it would be one. So you could normalize it differently so that we would just say like self-relatedness of diploids should be one. But I wanted to kind of have a common definition that applies to haploids and diploids and can be used for haplodiploid in, you know, society or something like that. So that's why it's Sally.
I think I blinked at the wrong time. And one thing I really like the idea of these expanding sets, and that allows you to see what the benefits come from larger and larger collectives. So when I blinked was, so in that set, there can be genetic variation in heterozygotes and homozygotes. And I didn't understand how you attributed to each of their fitnesses. There's diversity within that set.
Right.
And what happens, because there can be things like underdominance or overdominance in the cooperative behavior.
Okay. So the kind of simple answer is that, so all those effects can happen. There are always, no matter what effects are going on, there always is that polynomial representation of like, there's some linear effects, there's some quadratic effects, there's some cubic effects. You can write down a polynomial that kind of incorporates all of that.
Of allele frequency within the set, what's the polynomial of?
It's a polynomial of fitness as a function of who has what allele. So it's not just allele frequencies, because it's the alleles are tied to specific sites in the population. It's not just, you know, how many have this allele, but does where they are spatially, how they're arranged in individuals, things like that. That polynomial can be very complicated. It's not always easy to break down, but we know it always exists. Yeah.
So one of the slides you said you were going to unify these different multi-level selection, inclusive fitness. So this is a really nice result on the inclusive fitness side. But if you're looking at the power set of all individuals, then that suggests that in general, there's no hierarchical structure where you should be able to ask this in multi-levels. Is multi-level selection framework inherently more limited, I guess, than some sense, because it doesn't allow for these overlapping sets of actors.
Right. Yeah, I mean, I would agree with that. Like, I think having overlapping sets and actors is important, or just overlapping, you know, social associations, right? You know, that is important. And to the extent that multi-level selection models exclude that, I would argue that, you know, this is more general, those are limiting. I guess the integration part was that I think this can play well with existing models of multi-level selection, and you'll get, like, you know, the terms for the specific levels will be meaningful when you write out these polynomials. Yeah.
So do these this approach, I mean, it's really nice. It's curious, kind of related to these sort of sortativity measures of relatedness, and what I'm seeing, I think, is that this would reduce to those in the special cases where I was willing to delimit the sets that I was looking at. Is that right? Is that how that would behave? So it is fundamentally, it is another kind of a sortativity approach, but what it's doing is expanding beyond saying, oh, it's a sortativity between me and my neighbor, and that's the only thing that matters, because of my coalition and my neighbors, and all of these are sortativities. Together,
right. I think that's true. And the relatedness, it's a statistic of a sort. So it's defined in terms of basically, you know, identity by state. Yeah.
So did I understand correctly that neither the C nor the R parameters depend on the mutation rate?
We're taking mutation to 0 in all, in all the stuff I've shown you. It's at the limit of mutation rate goes.
So the results are really, mutation this.
Yeah, I didn't consider non-zero mutation in this work. I think I would know how to do that in a follow-up work, but I haven't actually.
But it's mutation going to, it's not actually 0, there is enough mutation to maintain the equilibrium.
Yes. Right. So it's, yeah, we need some mutation to have a stationary distribution, but then, yeah, when you take it to 0, again, that's when all these things are defined.
I'll just give you the, wait a second, in the framework, you can't get, it flipping, which allele is favored by increasing the mutation rate, which you think, altruistic behavior should become disfavored as the mutation rate increases. Now I understand, because you're assuming the mutation rate is so low, below all that.
Right, yes.
Okay, I think we better stop. So. I don't know, I guess maybe let's come back.